Guys, so I didn't have a lot of time to go over any if you had any questions. So what I decided to do was make this video of me working out this problem for you. When I look at this problem, it says the figure above shows the temperature of a 1.00 kilogram of ice, which is water. So that's the first information I've been given. So I like to write all my numbers down. So kilograms of water. I know that I'm not going to be able to use kilograms. I need to convert that to grams. I'm going to use Kevin hates dates because dates cost money, and convert those kilograms. I need to move the decimal place over 1, 2, 3 places. So that's going to give me 1,000 grams of water that I'm going to use for the mass on all my problems. The next thing, it says that it was starting at negative 20 degrees Celsius. So the initial temperature is negative 20 degrees Celsius. It's heated at a constant rate of 100 joules per second. I'm not going to worry about that right now. After about 8.5 hours, the ice has become water vapor, which is still water, at 120 degrees Celsius. So I'm going to end at 120 degrees Celsius. Remember, this decimal makes that number count as 3 significant digits. There are 5 distinct regions on the curve, each of which has an arrow nearby. Above each arrow, write what is happening, right? So they try to give you an example, but I'm going to write them out here. So we have a tiny one. Okay, so I'm going to draw those arrows, and I'm going to use different colors to represent each stage. So we're going to start here at the bottom. So what's happening at this first arrow is that, right, the ice is warming. Right, we're heating that ice up. At this second stage, right, at this one, we're going to have ice melting, which means becoming liquid. When I change a state, I don't change temperature. That energy is used to separate those molecules. At my third stage, right, this one it's kind of longer, it takes longer to do, right, the liquid is warming. And then as we get warmer, right, that liquid at this stage, at this line, the liquid is going to vaporize. Remember, vaporize means to become a gas. Then the last arrow is where the vapor is going to be warming. So these are our 5 distinct regions on our graph, and each of them corresponds to a different formula. Now, the ones where we have a change in temperature, we're going to use the same formula. So that's going to be in number 2 on the question. It says below each line, write the algebraic equation that's used to calculate the heat for that region. So for ice warming, we're going to use Q equals M Cp delta T. And anywhere we see warming, that change in temperature, we're going to use that formula. Now those specific heats will change, but the formula stays the same. Then at the other regions, right, the ones where they're flat, the ice melting and the liquid vaporizing, we're going to use specific formulas. So when the ice melts, Q is going to equal the mass times delta H of fusion. And when the liquid vaporizes or becomes a gas, Q equals M times delta H of vaporization. So now we have the information we need to do part 3, which is answering the question, how much energy is it going to take for 1 kilogram of water. They always make announcements, right? Okay, so number 1, we're going to start here at the ice warming. So we're going to use this formula. Let's scoot this over. So Q equals mass times CP times delta T. My mass is 1,000 grams, but remember that's 3 sig figs from our 1.00 kilograms. The specific heat of ice, you're going to have to look at this part of the question where it says use the table below. These numbers are slightly different than the ones I used today in class, but the results are similar. So the specific heat of ice is 2.11, and my change in temperature, my final minus initial, will be 0, right, because that's when ice melts, minus, and I'm starting at negative 20. So 0 minus a negative 20 gives us a positive 20.0. Right, we've got 3 sig figs up here. So that when I get this answer, right, 3 sig figs, 3 sig figs, 3 sig figs, I get 42200 joules. So 42,200 joules. For the second part of our graph, we have ice melting, so I'm going to use Q equals M delta H of fusion. My mass is still 1,000 grams, and my delta H of fusion is 333.6. Again, this mass is to 3 sig figs, so to 3 sig figs, I get 334,000 joules. For step 3, we're at liquid warming. So now we're going to use, again, Q equals M CP delta T. The mass is still 1,000 grams. The CP is 4.18 according to our table. And the change in temperature for ice to go from here up to here, right, if we look at our graph, is from 0 to 100 degrees Celsius. So we're ending at 100 minus 0 gives us a change of temperature that is 100 degrees. When I multiply these together, right, I still need 3 sig figs based on my mass. So that's 418,000 joules. At step 4, right, we're getting almost to the finish line. We're at the liquid vaporizing and becoming a gas. So I'm going to use this formula, Q equals mass times delta H of vaporization. My mass is still 1,000, and my heat of vaporization I get from the table is 2256. To 3 sig figs, my answer should be 2,260,000 joules. That leaves us with our very last one. So now we're at the vapor warming. So I'm going to use this formula, and I have to remember I'm stopping at 120 degrees Celsius. So Q equals M CP delta T. My mass is 1,000. The specific heat of vapor, look at the table, is 2.08. And the change in temperature is 120 minus the 100 that we ended at when we vaporized the liquid. So that, again, gives us 20 degrees. So when I multiply 1,000 times 2.08 times 20.0, again I get 3 sig figs, and I get 41,600 joules. Then to finish this whole fun time off, I've got to add all my Q's together, and I get 3,095,800 joules. Remember, when we're adding, it's not the number of sig figs, but the number of decimal places. None of these numbers have decimal places, and neither does my answer. Okay? Tomorrow we're going to have lab, and then you're going to have some of these problems for homework over the weekend. I'll see you tomorrow.